Again, welcome to Mathematical Structure for Computer Science, CS 113, also called the Discrete Mathematics. So this will be our last lecture for algorithms, the topic algorithms. So this is our part 3 lectures. We have 3 lectures in algorithms. The first lecture we discuss about what is an algorithm and the whole concept behind it. How do we develop an algorithm? Then the second part, we talk about how do we measure an algorithms using the big O notation and also the big theta notation. In this session, so we're going to discuss about the complexity of algorithms. When we say the complexity of algorithms, we mean to say the time complexity and also the space complexity. So time complexity is to measure how fast the algorithm runs. So we have to use the big O notation or big theta notation to measure it. Then also the space complexity, we want to measure how much memory the algorithm uses to perform its tasks. So our main objective is to go through what is the time complexity, also the worst case complexity, the algorithm paradigms, and also understanding the complexity of an algorithms. So here we say that given an algorithm, how efficient is this algorithm for solving a problem given input of a particular size? Now, in order to answer this question, we have to know how fast the algorithm runs and also how much memory the algorithm uses. Now, the most efficient algorithm uses less memory and also run very fast as possible. So when we are designing our algorithm to solve a problem, most of the time, again, solving a problem, there are so many ways we can solve one problem. So we can write more than one algorithm to solve just one problem. But our goal is that we want to have an effective or efficient algorithm, which will take less time. It will run very fast, less time, and also which will take a less memory. So here we said that in order to know how efficient the algorithm is, we have to measure the time. So how much time does this algorithm use to solve a problem? We also have to know the memory size. So how much computer memory does this algorithm use to solve a problem? Now, when we analyze the time the algorithm uses to solve the problem, we use the term time complexity. As we said earlier, time complexity of an algorithm is we want to know how long or what time the algorithm used to solve the problem. Now, when we talk about space complexity, we want to measure how much memory the computer used to solve the problem. So time complexity and space complexity. But in our textbook, we cover only the time complexity. So in this course, we focus on time complexity. So we will measure the time complexity in terms of a number of operations an algorithm uses, and we will use the big O or big theta notation, which we again discussed in the previous lectures. The big O and big theta notation are used to estimate the time complexity. So an example is, let's say we have a search algorithm, which we discussed in previous lecture. There are two types, the binary and the linear. Now, how can I know the two of them, which one is efficient? So in this case, we have to know the number of comparisons we make. We said the linear, we have to start from beginning to the end. Search. So the worst case would be if the item we are looking for is at the end. The best case would be if the item we are looking for is in the front. Now with binary, we don't need to go through all the items from beginning to end. First, we make sure the items are sorted. Second, we get the middle value. Then we compare the middle value with the search key. And the best scenario will be if the middle value matches the search key. If not, if it's greater, then we go to if the search key is greater than the middle value, we go to the upper side. If search key is less than the middle value, then we go to the lower side. Then we have to start all over, look for the middle value, break it into two, and keep going. So in the process of these two algorithms, linear search and binary search, how fast both algorithms perform is to measure the number of comparisons we do with the search key and the element in the list. So here we say we can use this analysis to see whether it is practical to use this algorithm to solve problems with input of a particular size. And the input is very important. In measuring algorithm, the more input you have, most likely, the more time the algorithm will take to solve problem. The less input you have, the less time. And also, it will depend on our computer. If we have a very good computer with a very good, powerful CPU, most likely to take lesser time than if we have, let's say, 10 years old computer, a very old computer with less speed CPU to take. So in order to measure an algorithm, first we have to make sure the number of inputs are the same. If I want to compare two algorithms, which one is faster? The input to both algorithms should be the same. Also, the algorithm should run on the same machine, not different machine. So here, we have to ignore implementation details, including, let's say, the data structure used and both the hardware and software platform, because it's extremely complicated to consider them. So in our textbook in this course, we are going to only focus on the algorithm itself to see how many comparisons we make or how many operations we perform, arithmetic operations. The time complexity also not only comparison, but also it can depend on the number of operations, example, number of arithmetic or logical operations we perform. But in this textbook, again, we are not going to discuss about, okay, the hardware should be the same, or even the software platform. Sometimes some will be more effective, some will not be effective. So all this can, again, affect the speed of the algorithm. But in this textbook, we're going to focus on the mathematical aspect here. So we shouldn't consider the hardware and also the software platform. So in order to analyze time complexity of algorithm, first we need to determine the number of operations, as we said earlier. And operations can be comparisons or arithmetic operations such as addition, subtraction, division, etc. We can estimate, again, we also need to consider the hardware and also the software platform. But again, this section, in this textbook, we are going to ignore that part and focus more on mathematical aspect to analyze. So here we can estimate the time a computer may actually use to solve a problem using the amount of time required to do the basic operations. As we said earlier, we are going to ignore the minor details, such as housekeeping aspect of the algorithm. And we will focus on the worst case. Now, a worst case time complexity means, for example, if I'm doing, again, searching, the worst case would be my search key will be at the end of the list, or my search key is not even in the list. Because if my search key is not in the list, it means I have to do all the total comparison to the end. Now, if my search key is in the list, let's say third position, it means I'll do only 3 comparisons. Because after I find the item, I'll return it. I'll stop looking. So the worst case will be at the end, or the worst case also will be the item I'm searching for is not in the list, so I still have to go up to the end. Now, the best case scenario will be the items is in the front of the list. So I have to do only 1 comparison. Again, also we say it's usually much more difficult to determine the average case time complexity of algorithm. The average case here will be the middle. How many number of comparisons we have to do in order to reach half of it? So example is given here, complexity analysis of algorithm. Here they say we should describe the time complexity of the algorithm for finding the maximum element in a finite sequence. So finding the maximum element in a list, let's say find the maximum value in a list of 10 values, it's more or less like searching for an item also. But this time you have to be linear search. Binary search, remember, the item have to be sorted before we even start all over, before we start. But finding the maximum element, if the list is not sorted, we just have to start from beginning. So we can see the algorithm here. Again, the algorithm name is mass. Again, this is the syntax of writing an algorithm. So we can start the keyword procedure means it's a function or a method. Then we have the name of the function is mass. The argument is to take the information. In this case, the list of the item. If it's in an array, then we can have array here. Then the size of the array. So now we know the algorithm already for finding the maximum value in a set of values. The first value in the list, we will consider it as the maximum. Since we are going to repeat the comparisons, we need a loop. So here they decided to use the for loop. Since we already said that the first item is the mass, we start with the second item till the end of the item. Then we are going to compare the first item with the second item. If the mass is less than second item, then what we need to do, we have to assign the second item to the mass now, because second item is greater than the mass, so you have to be the new mass. Then we have to repeat this till the end. Here we are using recursion, so you can see this is our base case. If we didn't find it, then we call the function, we call itself reduced by 1 till we reach our final stage. So here the solution is given here. Now they say here, we want to analyze this algorithm, how fast it is. So the first thing we're going to do is count the number of comparisons that we have to make. First, we saw that the mass is less than the second item. The first item is mass, it's less than second. So here we say the comparison is made n minus 1. Why n minus 1? Because we take one element already as our mass, and we are not going to use it. So the rest will be from 2 to n, so it's n minus 1. Now we say that each time I is incremented, a test is made to see if I is less than or equal to n. Now the one last comparison will determine if I is greater than n. So in average scenario, we have 2. First of all, we have n minus 1. So when we get n minus 1, we multiply it by 2. Then we add 1 to it, which is our first value. So here, the total comparison here will be 2n minus 1. Why 2n minus 1? First, we know n minus 1 means we take the first value as the mass, so the rest of the value will be less 1. So this means I'll take the first item to compare all the items, which will be n minus 1. Then I will add the actual one from beginning. And also we have to double twice of n minus 1 twice. So the worst case complexity of a linear search, a worst case of complexity of linear search is 2 options. The item is not in the list, or the item is at the end of the list. So this is linear search again. We went through this in the previous lectures. So here we have our S values, A1 to AN, then the integers. We assign our, I will be our, I'll use the term variable to count the items in the loop. So here we initialize our count to 1. Then we say if I is less than n or I is less than or equal to n, which means we still have item in the list. For example, if we have only one item, then I will be 1 less than or equal to 1. We work it. When we increment to 2, it's 2 less than or equal to n, so we stop. So here, the list of the item, the size is n. So we say, okay, I should be less than or equal to n. N, s is not equal to a, I. Then we increment. Now we said that, okay, if I is less than or equal to n, which means we still have items in the list, then we have to find the location. Now, if this condition is false, then we said assign location will be 0. So we return location, which is location is the subscript of the term that equals to x, or is 0 if s is not defined. So this is the solution. We count the number of comparisons. At each step, we have 2 comparisons that are made, which is I is less than or equal to n, and also s not equal to ai. 2 comparisons are made here. Then we say to end the loop, 1 comparison I less than or equal to n is made. Then after the loop, 1 more I less than or equal comparison is made. So this means if s is ai, then we get 2i plus 1 comparisons are used. If s is not on the list, then 2n plus 1, which means we go in, it's not in the list. We have to look through the list to the end. So the worst case will be 2n plus 2. So let's see the average complexity of the linear search. So here we say we describe the average case performance of the linear search algorithm. Although usually it is very difficult to determine average case complexity, it is easy for linear search. Here we are assuming the element is in the list and that the possible positions are equally likely. But the argument on the previous slide, if s equal to ai, the number of comparisons is 2i plus 1. So here we have 3, 5, 7, all the way to 2n plus 1. Then we go through the list from 1, 2, 3 up to n plus n. So in average case, we get n plus 2. And then we don't need to, again, if you are using a big O or big theta, we don't need to worry about this constant value because the higher the beginning, let's say n is 1, yeah, then the 2 is important. But when n becomes 1,000, it still is important, 1,002. But when it becomes million plus 2, I mean, the difference is very big. So that's why we say S, the average case complexity of linear search is theta and n, not n plus 2. So this is a worst case complexity for binary search. They say we should describe the time complexity of binary search in terms of number of comparison used. Remember, binary search, first we have to make sure the items are sorted, then we can find the middle value. And that's what we did here. Make sure the 2 items are sorted, then we get the middle. Now we compare the middle with the lower left side, if the search key with the middle. If the middle is lower than the search key, we go to the lower section. If the middle value is greater than the search key, then we go to the upper section. And that's what statement we have here. So here we say, assuming for simplicity n equal to 2 to the power k elements, we should know that the k equal to log base n. So 2 comparisons are made at each stage. We can see the I is less than j, and also s is greater than am. So those are the two comparisons. At first iteration, the size of the list is 2 to the power k. And after the first iteration, it is 2 to the power k minus 1, then 2 to the power k minus 2, and so on. Then at the last step, the comparison tells us the size of the list is 2 to the power 0, which is 1. And the element is compared with the single remaining element. Hence, at most, it will be 2k plus 2, which is the same as 2 log base n plus 2. And this is a bubble sorting. We talk about bubble sorting, that in bubble sorting, we take the first element compared to the next. If it's greater, then we swipe it. So we are swiping and get a greater value to the back. Then we start all over again. So the first comparison, it depends on the position and also the value. But the first comparison, we have to do the number of, that's the size, which is the number of items in the list, minus 1. And that's what we have here. But let's go through the algorithm. So we have bubble sorting the items with n greater than or equal to 2. So the first loop is the number of items. Second loop, we are going to compare the first item we pick to all the rest of the item. So second loop allows us to do the children or the list of the items. Now, if aj is greater than aj plus 1, which means the first item is greater than the second, then we have to do swiping. Oh, here we use the term interchange aj and aj plus 1. So the solution sequence of n1 passes is made through the list n minus 1. Because again, as we said, the array, we go from n to 1 to n minus 1. Then after we find the next, you see that we are in the first loop. Condition is true, we go here. Then we do n minus 1. Then when we increment to 2 here, so it will be 1 more less. That's why it's n minus 2. The n minus 3, n minus 4, to be every round it to be lesser. Because after we get the highest and we bubble it to the end, we are not going to compare the value to it no more. So reduce by 1. Next time we bubble the next higher, so 2 items. So the comparison will be n minus 2. And that's what we have here. By doing the calculation, we get half n squared minus half n. And as time goes on, when n gets greater, you see that the half and n is irrelevant. So normally we say that the bubble sorting was an error. The bigger notation is n squared. With the searching is n. We have another example here for matrix multiplication algorithm. So here the definition for matrix multiplication can be expressed as algorithm C, matrix A times matrix B, where C is an n by n matrix. That is product of n k matrix and the k n matrix B. And this is the algorithm. So we start a for loop with our rows and columns. So from 1 to m, 1 to n, and we find our first Cij will be 0. Then we say for q is 1 to k, and Cij is Cij plus iq pqj. So how many addition of integers and multiplication of integers are used by matrix multiplication algorithm to multiply two n by n matrices? The solution will be n squared. And also finding the each entry require n multiplication and n minus 1 addition. And so we have n cubed multiplication and n squared because it's n squared times n minus 1. So it will be n cubed minus n squared. Again, as n become bigger and bigger, n cube will be more important, and n square is irrelevant. So that's why we say the time compressor of matrix multiplication is big O n cube. So the algorithm paradigms, we say an algorithm paradigm is a general approach based on a particular concept for constructing algorithms. So the general approach based on a particular concept for developing or constructing algorithm to solve a variety of problems. So we have, for example, the grading algorithms. We have the heuristic type of algorithm, brute force algorithm. So here we say grading algorithm were introduced in section 3.1. That was our first lectures on algorithm. We also discussed the brute force algorithm in that section. And we also see the divide and conquer algorithm, but we didn't go detail. We also have dynamic programming, backtracking, probabilistic algorithms. So if going to focus on maybe something like machine learning or data science, and the most common algorithm we're going to use will be the probabilistic, heuristic, and divide and conquer algorithms. Dynamic algorithms also is used a lot in bioinformatics problems. So brute force algorithm means it's solved in the most straightforward manner without taking advantage of any ideas that can make the algorithm more efficient. So brute force means I'm solving a problem. I'll just go ahead and solve it in any. I don't care about which direction to go, which will be more quicker, but just solve the problem. So brute force algorithm we have previously seen as sequential search. Sequential search, we don't care. We start from beginning to the end. Or bubble sorting, we still have to start from beginning. We take the greatest, the bigger values to the end. And then section sort also. Now the computing the closest pair of points by brute force, we're going to compute closest pair of points by brute force. So first construct a brute force algorithm for finding the closest pair of points in a set of endpoints in the plane and provide worst case estimate of the number of arithmetic operations. So the solution here, if we work, we can record that the distance between SI, YI, and also SJ, YJ, remember our Pythagoras of formula for finding the distance between 2 points. I take the two S's, difference of two S's all square plus difference of Y, the two Y's all square. And understanding the complexity of algorithms, again, these are using the big theta. So big theta 1 is a constant value, so this is called constant complexity. Big theta log n, this will be logarithmic complexity. Big theta n will be linear complexity. Then big theta n log n will be also linear arithmetic complexity. Then n to the power b will be polynomial, b to the power n exponential. Why is it exponential? Because again, this time we have n, which is the variable as our exponent. Then we also have a factorial complexity. So this is an example. Let's say we have a problem, the size is 10. If it's log n, it will be log base 10. Base 10, 10. Now, if it's 10 squared, to be 7 times 10 to the power negative 11. N will be 10 to the power negative 9, etc. So we have something we call the tractable problem. Tractable problem is if there exists a polynomial time algorithm to solve this problem, this problem are said to belong to the class P. Intractable problem means there does not exist any polynomial term algorithm to solve this problem. Then we also have unsolvable problem. This means no any algorithm exists to solve that type of problem. Then we have the class NP, which is solution can be checked in polynomial, but no polynomial term algorithm has been found for finding solution to problem in this case. Then NP complete class. If you find a polynomial term algorithm from one member of a class, it can be used to again solve all the problems in the class. So we're going to end in the session here. In this session again, our main goal focus on time complexity. And what is a time complexity? How do we measure the effectiveness or efficiency of an algorithm? As we said, it's based on two things: the time complexity, how fast the algorithm works, and also the space complexity, how many memories you use. But in this course, we are not going to discuss the space complexity. We're just going to focus on only the time complexity. In this case, we use the big O notation and also big theta notation as our tool. So again, wish everybody the best. Thank you.